Statics in 3D, we have the same two basic equations. The first of which is F net equals 0. So it's not accelerating in any direction. And what does that really mean though when we talk about in in 3D? Well, that means that some of forces in X and some of the forces in Y and the sum of the forces in Z are all 0. This is translational equilibrium. It doesn't mean it's sitting still, although usually that's what we're after. It just means it's not accelerating, right? It's just not accelerating. The same thing is true for rotational equilibrium. The sum of all of the torques are 0. And that, again, in torque, we haven't talked too much about torque being in more than one dimension, because we're usually talking about stuff in a plane that only rotates around one axis, or can only potentially rotate around one axis. But when you talk about torque and rotation, well, rotation in the XY plane is a torque along the Z axis. Rotation in the YZ plane is a torque along the x-axis, and rotation in the ZX plane is a torque around the y-axis. And what does all of this kind of look like? We'll get to actual problems, but what does this kind of look like when we look at like an image? So I'm going to take this table picture we have, and I'm going to put books here, and I'm going to put books right there. Now, the static problems we did last time were really just go along, call one edge X, and we're going to calculate what the forces are in X, and we're not worried about where things are in Y. If um, we call this direction X, and we call that direction Y, and that makes Z that way. Okay, so now we have some X, Y coordinates for this and X, Y coordinates for that. And we can even say we have Z coordinates. If we call this the origin, and we're talking about this table, well, down here we have the legs, and back there you can't quite see them. You have the legs and everything. And so you have the weight of this, you have the weight of this, and you have the forces upward from the floor. And all of those have to, and then there's the table mass, which we'll presume is along the center of the table. It may or may not be right up there. Glass is heavy, so it's probably close to the glass, but that's where the table mass is. And so um, what you do is you write down the X, Y, and Z coordinates of all of this. You'd calculate for this has a minus Z force, this has a minus Z force, that's a plus C, plus C, plus C. So in some sense, this is still one-dimensional in that the forces are all in Z. There are no forces in X and Y. But the fact that you have in this direction along X, you have this times its X position plus this times its X position equals these forces times their X position. And then you've got to look in Y and look at the Y position and the forces in the Y direction times their position. And so and that's when you're talking about torque, right? So some of all of the weights and the forces off the floor have to be 0. All right, so this mass or this weight plus that weight has to equal that force plus that force plus that force plus that force. Well, and you have to add in the weight of the table, right? I'm forgetting that. This table is going to weigh something. You have to add in the weight of the table. And then on the torque you have to do along X and along Y to get all the torques. And that's going to give you everything you need in order to sort out what all the forces on all of these pieces are. And you got to pay attention to, the center mass of the table is going to give you an equal force on everything and all of that. So, all right. But that's it for what we mean by simply extending into more dimensions. Now you have to look at torques in along the x-axis and y-axis, and you have to look at forces in multiple dimensions. We'll get into some problems on this. It won't be too difficult once you see how to do it. All right, that's it for the 3D.